Right, everybody, thank you very much for everyone for coming. It looks like we've got a great turnout today for a terrific visitor. Today I'm very happy to introduce Dr. Rebecca McElroy from the University of Southern Queensland, where she is a tenure-track Women in STEM Fellow. Rebecca did her undergrad and PhD at the University of Sydney, followed by a postdoc at the Max Planck Institute for Astronomy in Heidelberg, postdocs at the University of Sydney and a fellowship at the University of Queensland, and is now at the University of Southern Queensland working on changing book AGN. So, Rebecca, are you ready?
Sure. Okay. Hello, everyone. Hopefully everyone can see the screen. Let us know if you can't. So today I'm going to be talking to you about changing look, active galactic nuclei, and how we can use them as laboratories for black hole growth and evolution. But first, I am going to do a little kind of call out for, for where I work. So in case you don't know, I live in Sydney, so you're used to seeing me quite a lot. And I have an honorary appointment here, which I'm very grateful for. But I do work at the University of Southern Queensland, and you might say, Rebecca, this is very Southern Queensland at this point. And yes, yeah, I mean, the weather is certainly trying. But I do work at USQ, and I just wanted to tell you a little bit about our department before I get into the science. So we're actually quite a diverse group now. Previously, you would have known USQ as being very much focused on stars and exoplanets, but they've now hired me, and I do not do either of those things. And so we now have me, expert on galaxy evolution, time domain astrophysics, that's also me, and Jonty. But we also still have a lot of work on exoplanets, stellar astrophysics, solar system physics, and in particular connections with the Australian space industry through our iLaunch scheme, which is a partnership between, I think it's 4 universities and Optus to launch small astronomy-related satellites. And there's also a lot of astronomical instrumentation, which happens at our little observatory in Toowoomba. You might think that this is a very small department, but did you know that 2/3 of all JWST time awarded to Australians was awarded to USQ? So we are not, we may be small, but we are quite mighty. So feel free to come visit. We have lots of talks. And I just wanted to point out a couple of other things that may be of use to you. So we also have an observatory. This is Mount Kent Observatory, which I have drawn here. So when I wear my other hat, I'm also a digital artist. And if you like this, then come see me after and I'll give you a sticker. Am I UniSQ's marketing department? Mostly. I remember. Yes, so we can attest that it's a very good department. And so this is Mount Kent Observatory, which is Australia's second largest optical observatory after the AAT, of course. And it's an array of 5.7 to 0.5 meter telescopes. They're mostly used for stellar spectroscopy, exoplanet follow-up, that sort of thing. But if you have a project that could use these telescopes, please let us know. We're always keen to get involved with other people. We're always trying to get students involved, and it's a great experience to get to use a telescope. We also offer, I think, the only fully remote master's and PhD programs in Australia. So you might notice I am a fully remote staff member, and this is because we are a regional university. So we target regional Queensland and have 3 campuses across Toowoomba, Western Brisbane, and Brisbane. So if you, for any reason, for family commitments or for accessibility reasons, need a more kind of remote approach to a PhD, or you have a student who would benefit from that, then please reach out to us. Okay, that's the end of my little advertising segment. So we're going to start with a little bit of history. So back in the, I think this would have been the 1930s or so, astronomers were looking at nearby galaxies and observed that some, actually this is slightly later than the 1930s, I apologize, looking at some nearby galaxies like NGC 1068 and observing that they had strong and very broad emission lines. something like this. So usually emission lines look very spiky. These ones you can see have, quite broad bases. This tells you that there's something very fast moving going on, or there's lots of chaotic stuff going on along the line of sight. And these were coming from the very center of the galaxies. And the thing that puzzled people was that this was much more energetic than emission that would come from stars. So they were trying to figure out what could be causing this. And in typical astronomy fashion, named after some bloke, Seafoot, and so these have henceforth been known as Seafoot galaxies. Concurrent with this, radio astronomy was really taking off. And I like to highlight this because this is really an Australian story. So much of early radio astronomy was happening in Australia. And if you really feel like taking a tour down kind of astronomy history, you can go and see one of the first ever radio antennae. Just off the kind of Bondi to Coogee coast walk, you can see a model of, is it a duplicate? Like a replica, that's the word we're looking for, of the first radio antenna in Australia that localized radio emission from the sun, I believe. But once they'd figured out the sun, they started looking at other bright sources in the sky. And anyone who's done radio observing will recognize this calling code, 3C273, which is a very bright radio source in the sky, often used as a calibrator. And they found that this very bright radio source coincided with a very bright optical point source. And so if you ever wondered where the name quasar comes from, other than, dishwashing tablets or whatever misappropriation of the word has been stolen, actually comes from quasi-stellar object. So it does what it says on the tin. This is a thing that looks like a star, but is also emitting in the radios. We're not really sure what's going on. So they had really weird spectra with very strong, unidentified emission lines, something like this. Again, you can see they're very broad, but they didn't line up with any known emission lines that people were used to from lab experiments. So just to recap that, we've got Seafoot galaxies and quasars. Seafoot galaxies have strong and broad emission lines in the centers of galaxies, much too energetic to come from stars, even young ones, and have a spectrum that looks approximately like this. Quasars are point-like, so they look like a star. And they also have these strong unknown emission lines and look like this. So there's a really good story about how somebody figured this out. There was a lot of staring at things on blackboards and looking at, printouts, or I don't know, how did they print things back then? Anyway, but eventually they figured out that the emission lines were the same. They were just much further away. So these two objects are actually the same phenomenon. Just one is much further away and much brighter. So when you de-redshift the spectrum, these lines line up. And so both of these things are powered by accretion onto a supermassive black hole, which is the most energetic sustained process in the universe. And to batch them all together, we now mostly call these active galactic nuclei. And we have many different types of these things. So we still have quasars. These are things that are very bright. Seafoots, which are things that are nearby. You can still see the host galaxy. Radio galaxies are the ones you can see in the radio. Blazars have a jet pointed towards you. And there's all sorts of different ones. So, active galactic nuclei. In the center of galaxies, there's a supermassive black hole, which is millions to billions of times the mass of the sun. Even our galaxy has one, Sagittarius A star, which is about 4 × 10⁶ solar masses. And when there is fuel around the black hole, eventually it will fall in. And this is what causes the nucleus to become active. This is enormously luminous. As I said, can outshine entire galaxies and is the most luminous sustained process in the universe. So why do I care about active galactic nuclei? As I said, most energetic process in the universe. So, it's got to be important, right? If there's that much energy coming out, where's that energy going? What's it doing? And as one might expect, it has an important impact on how galaxies evolve. So we have a galaxy here, obviously an approximation of a galaxy, not a real one. And we turn the nucleus on. This dumps a bunch of energy into the rest of the galaxy. So energy from the nucleus heats up gas within the galaxy. Now, if you remember how star formation works, the gas needs to cool down and fragment to form stars. So if you dump a bunch of energy and heat the gas, you prevent this from happening. So this means that we posit that AGN can slow down star formation in galaxies. People often call this quenching. You might have heard this as a buzzword in a lot of abstracts. In addition to that, it can push gas out of the galaxy. And so this is directly starving the star-forming reservoir of fuel by just pushing stuff out, taking away the fuel that could have been made into stars. So what actually is an AGN? I've told you it's the active nucleus of a galaxy, but what's going on there? In the very center, you have a supermassive black hole. That is the black dot in the middle. Surrounding it, we have an accretion disk. So this is the disk of stuff that has been sufficiently unlucky to get trapped within the gravitational sphere of the supermassive black hole. Because the gravitational pull is very strong and it's very dense, this area gets really hot. And so all of this matter is essentially heated up, turned into a plasma. And that is where the extremely bright nature of AGN is coming from. Beyond the accretion disk, we have clouds of gas that are orbiting the accretion disk and the black hole, which may serve as fuel as they kind of make their way down onto the accretion disk. This is called the broadline region, and I can give you, you can guess why we call it this. We call it this is because where the broad lines come from. And the reason they're broad is because they're moving very quickly. So these gas clouds are close to the black hole. That means they are experiencing very strong gravitational pull. So they are moving very quickly around the black hole, and this is broadening the emission from them. Beyond that, we have some kind of torus. And depending on who you ask, they will draw this differently. So the torus is a opaque-ish structure surrounding the black hole and the broadline region, which obscures emission from these two regions, depending upon where you're looking at it from. We think that this is very dusty, and it reprocesses a lot of the light into the IR. But yeah, the exact structure is still a little bit uncertain. Beyond the torus, we have the narrow line region. And again, I bet you can guess why we call it this. This is where the narrow lines come from. And the reason they're narrow is because they're further away. So because they're further away, they are moving less quickly. So the lines are less broadened, okay? So just to recap, this is the structure of what we have. In the center, a supermassive black hole, surrounded by an accretion disk, depending upon how much matter there is. And then a broad line region, a narrow line region, and a dusty torus. This is called the unified model of AGN. It's been around for quite a while, has its limitations. We'll get to that momentarily. So if I look at this structure from this angle, so we're imagining that where these kind of lines coincide, we've got a telescope at this angle. So if I'm looking at this side on, the torus is blocking light from the accretion disk and the broadline region. So that means the only part of this that I'm seeing is whatever is re-radiated from the torus plus emission from the narrow line region. So you'll get a spectrum, something like this. So you've got the host galaxy underneath. I can't remember if I drew some accurate stellar absorption lines there, but maybe. And you get these narrow lines on top, highlighted in pink here. And in particular, these are, Balmer lines, H beta, H alpha, but also forbidden emission lines, O3, S2, and N2. So we call this a type 2 AGN because we're really uncreative. we turn this system around and look at it from this angle, we have a type 1 AGN. So in this orientation, I can see the narrow line region, I can see the broad line region, I can see the accretion disk, and even the continuum emission from the accretion disk. So the continuum looks like this. It's very blue. It peaks in the like UV. So if you have an optical spectrum, it tends to look very sloped. We have the broad lines, which you didn't see in the slide before, which are broad, as the name suggests. And then again, we have the narrow lines on top of that. So that's the kind of schematic of where each of these components are coming from and what the spectra will look like. So just so you can compare the two, the main differences between type 2 and type 1 are there's no broad lines in type 2 AGN, and there's no continuum emission. If you want to be slightly more descriptive about what these are called, instead of calling them type 1 and type 2, you might also hear people call them unobscured and obscured, which is much better, right? So in a type 1 AGN, nothing is obscured. I can see emission from everything. In a type 2, a bunch of stuff is obscured. I can only see the narrow lines. Okay, so you've had your recap on AGN, but I said I was going to talk about a specific type of AGN, changing AGN. So this is not new. We've known AGN vary since we discovered them, particularly in the radio. They noticed that they were varying on days and weeks timescales almost as soon as they were observed. There's also been statistical analysis that shows that accretion onto supermassive black holes has a duty cycle that causes flickering on 100,000-year timescales. I already said that, I apologize. But a particular subset of AGN, so what we were talking about there is just kind of garden variety varying a little bit over time. Changing look AGN is much further beyond this typical AGN variability. This is very dramatic. It causes brightening and dimming by large factors and can also facilitate changes between the two spectral types that we talked about before. So when something changes in brightness sufficiently, you can actually observe a single AGN to go from something that looks like this to something that looks like this. This is a very rare phenomenon. There is quite a range here, you will notice, and that's because they're not observed in a systematic way. We only find these things randomly. And so you can ask me in approximately 2 years' time how rare they actually are, once LSST has, done a bit of stuff. So why are these important if they're so rare? They challenge the unified model. So this unified model was first kind of put together in the 90s. So it's about as old as me. And this particular subset of AGN really does challenge this, because obviously we're not seeing a rotation of the central nucleus. The dynamical timescale doesn't allow for that. And we're not changing our viewing angle. So something else has to be going on. Specifically, they imply that there is more to accretion than we know. And accretion is really important, not just for AGN, but for stars, for planets, for everything. Everything accretes, has to start somewhere. But the most important thing is, unlike everything else in galactic astronomy, is we can do this on human timescales. So we are incredibly lucky that changing look AGN vary on kind of year, decade timescales, which is crazy because these things are billions of times the mass of the sun. So unlike most other work that looks at supermassive black holes, we actually get to see real-time evolution of these systems. This means that we can actually see how they evolve over several years and use them as a direct test of our understanding of accretion physics. So this allows us to probe how black holes grow, which is one of the most kind of unsolved things in the universe, on accessible timescales. So today I'm going to talk to you about my favorite galaxy. And I think it's important to say that I have been yapping about this galaxy for a decade at this point. So don't talk to anyone at CIFA about it. So this is a late stage merger remnant. So if you're not a galaxy person, the reason we can say this is because it looks weird. Galaxies tend to be symmetrical. This one is not. You can see that there's like some spiral, some tidal features here. There's like a wing around there, and there's a little companion falling in. I'll just circle that so people online can see. So we've got some tidal features and a companion falling in, kind of an arm around here. So this is a nearby-ish galaxy at redshift 0.04. Oh, there's the next. It's a merger remnant. And we observed this as part of a MUSE survey. So this was actually one of the first large programs when MUSE was commissioned, the Close AGN Reference Survey. So we wanted to look at 40 unobscured AGN. And we had this as part of our sample, and that's how we discovered its interesting activity. But I'll take you back to its discovery. So in the 1960s, Benjamin Markarian did a UV bright galaxy survey, and that was when Markarian 1018 was first identified. What's its name? In 1979, the first spectrum was taken by, and it looked like this. So you'll notice that there is a quite broad line there. You might say, Rebecca, why is that being classified as a type 2? The reason is it has no continuum. Okay, there are intermediate types. I just didn't want to confuse everyone. If you want to know about the anyway, they should tell you that the unified model is not. It's not everything if you've got, intermediate stages. But anyway, we're saying this is a type 2. Then it was observed again by Cohen et al. In 1984. And the emission had changed substantially. So the big difference here is we start to see this very large tick up in the blue end. So this tells us we're now seeing continuum emission from the accretion disk. And you'll notice that there is a new broad line here that wasn't there before, and the broad line that we had before has also increased in brightness. So time passes, it's observed again by SDSS since stripe 82, still a type 1. It's observed by the Hamburg ESO survey, and that's our parent catalog for the Close AGN Reference Survey. So we observed it as part of a sample of type 2 AGN. This is quite a fun story because I was at ESO at the time for a kind of a busy week with lots of my colleagues from CARS. And we were kind of looking through all the data once we'd gotten it. And then we opened this data cube. We were like, did we look at the wrong galaxy? This doesn't look right. And there's another changing look AGN in the Markarian survey, which is already known, called Markarian 590. And it's actually at a very similar RA deck. So we thought we just mislabeled the files or something. But then, we checked again, and we found that, no, this galaxy had changed again. So it had gone back to this type 2 state. So what's going on here? Something is happening that is causing this AGN's brightness to dramatically modulate. So go up, go down. In particular, from this kind of mid-2000s spectrum from SDSS to 2015, the amount of matter in the accretion disk must have decreased a lot to remove all of that emission from the continuum, so that very blue emission. And this has to occur on very short timescales. The last observation in stripe 82 was in about 2010, and we observed it in 2015. So realistically, it cannot be something stochastic. It can't just be, the feeding evolved. And it also doesn't line up with the dynamical timescales for it to be something kind of internal to the galaxy that isn't kind of something changing. So the first idea that you might have is obscuration. So an easy way to reduce the amount of light coming from something is to put something in front of it. Ta-da. So this reduces the brightness, and you've increased the dust along the line of sight. And anyone who deals with dust will tell you that this reddens the light that's coming from the galaxy. And this is because of the preferential scattering of blue light. Oh, hold on. Oh, sorry. I thought there was another thing going to come up. But so interestingly, we actually didn't observe any reddening in the new spectrum. It didn't look like there was more dust along the line of sight. And we also did the deeper version of this, which is looking at the slope of the X-ray spectrum, which tells you about the amount of matter along the line of sight. And that also came back the same. So we can pretty conclusively say that it wasn't obscuration. The next one is kind of fun. It's a tidal disruption event. And this is just a little animation of what that might look like. You get a star gets too close to the supermassive black hole, falls onto the accretion disk, and is either torn apart or escapes. And what this does is it increases the amount of stuff in the accretion disk, and then either as it escapes or is totally consumed, that falls down again. This follows a very well-defined power law, because this is observed in smaller black holes. It's observed quite a lot in the radio as well. But most models show that the star is fully consumed within 5 years. So this doesn't really work for our two-time changing event. So the next idea is an interesting, slightly new model of accretion. So we were talking about how there's clouds whizzing around the supermassive black hole producing the broad emission lines. And so chaotic cold accretion posits that among these clouds, they're all kind of moving randomly under the potential of the black hole. You might end up with two clouds that have equal and opposite velocity. And then with some regularity, they'll collide. And then when they collide, their angular momentum can cancel out. And that is what allows them to fall or kind of rain onto the accretion disk, causing a brief spike in the amount of stuff on the accretion disk, raising the luminosity in a very sharp way. So I don't have any arguments really against this one, because it works for several other reasons. This process can self-regulate. So in the bright phase when the AGN is very powerful, a lot of energy is being emitted, these clouds get pushed further away by kind of radiation pressure. And that reduces the likelihood of infall. So as you get brighter, you decrease the likelihood that more stuff is going to fall in, and then the brightness goes down, the things get closer again, and then the likelihood can go up, kind of creating this kind of characteristic timescale of increasing and decreasing accretion. The most fun idea is interesting black hole dynamics. So imagine you have your accretion disk with your supermassive black hole, but this is a merger remnant, right? So we can posit that there might be a second supermassive black hole hanging about in the center of this galaxy. So if you have an accretion disk and then you have this very large object orbiting around with some period, then that could disrupt the flow of matter onto the accretion disk in a periodic way. So when the companion supermassive black hole gets closest, you would perhaps reduce the flow onto the accretion disk or disrupt the accretion disk entirely, depending on how close they are, and reduce the brightness of that disk. And so a final idea is that what if you had a recoiling black hole? So this is kind of the scenario from before, but fast forwarding a little bit. So you've got two black holes from your merger remnant. They've merged, but because of the remaining angular momentum of the merged black hole, this supermassive black hole has a recoil velocity within the center of the galaxy. So if that supermassive black hole that is kind of oscillating around the center of the galaxy starts accreting matter, then you can imagine that this motion may cause variations in what we see from the accretion disk. So to summarize, here are our options. We've got obscuration, which modulates the brightness but reddens the spectra. We have a TDE, which will increase the brightness, has a power law, but is really limited to kind of a 5-year timescale. We have chaotic cold accretion, where you have these clouds canceling each other out, which will increase the brightness and also has this ability to self-regulate. And then the final one is black hole dynamics, which can modulate brightness in a periodic way, but understanding this is quite difficult. We have to rely on simulations to figure out what's going on here. So we're getting rid of obscuration, we're getting rid of TDE, and so we're left with these two scenarios. And so there has been lots and lots of work on these two scenarios from various different groups. This last one here is our group, which is Thomas's paper, which was submitted to the archive last year. So you can ask him about this if you have any particularly hard questions. And there's also been lots of work on the simulation side, considering black hole dynamics. And there's lots of other ideas going on. So with the current data, it is a little bit difficult to disentangle what's going on. We've kind of ruled out some ideas, but we're still left with various theories that could explain it. And so the question that we asked last year was, what if we could look at a longer time baseline? And this is where DASH comes in. So this is the Digital Access to a Sky Century at Harvard collaboration, which have digitized more than 500,000 photographic plates from, I think it's 1880 to around 1990, and put all of this online and lots of interesting tools that you can use to look at data. The spatial resolution is actually quite good, and the astrometry is also done to Gaia, so you can look for your favorite source. They're also flux calibrated, though in a slightly odd band. Again, you can talk to Thomas about that. And so this was Thomas's honors project last year. And if you want to look at his paper, I think that QR code should take you to it. At least it did the last time that I made that QR code. So he found all of the detections in the archive, removed a bunch of the bad data, and this is kind of what it looks like. So you can see this does not look like the image I showed you before, right? Okay, we're acknowledging that, but it is detected, right? That is Markarian 1018, that tiny little smudge in the center. And it's calibrated against all the stars in the field, and Thomas did a lot of work to ensure that everything was done correctly to make sure that variability in Markarian 1018 was different to stars that he also did the time series analysis of. And so by doing this, he constructed a light curve from Markarian 1018's history. And so I draw your attention to the x-axis, which starts at 1910 and ends at 1990. And there's quite a lot of data here. And you might notice that there's something that looks like a fairly substantial change. So this is another, perhaps, changing look event in Markarian 1018's history in around 1935, which was previously unknown. So the next thing to look at is we don't just have to rely on plates. There are millions of observations of the sky. So what if we looked through all of them? So we looked at ZTF, the Catalina Sky Survey, Atlas, SDSS, and Assassin. If you've got any other favorites that you suggest we take a look at, let us know, or don't, depending on how much work you want to make Thomas do. And so we looked at all of these surveys, and Thomas made another light curve for after the plates. So this runs from about 2000, which is the SDSS Stripe 82, which I was talking about here, all the way to today. And so I'll just label a couple of things. So the 2015 change is this gap between these two samples. And yeah, okay, actually that's all I wanted to say. There's also, there's an outburst in 2020, if you look really close. There's a paper about that as well, which I didn't talk about. So there was a very small outburst in 2020. It's I guess the only interesting thing that happened that year. We don't talk about anything else that happened then. And so combining these together, Thomas made this amazing light curve. And I think this might be the longest baseline light curve of any active galaxy, running from 1910 to 2025, which I think is pretty incredible in and of itself. And so what he did here is he calculated an average of the kind of high state of the galaxy and the low state of the galaxy to categorize the historical data into two states. So we posit that before 1935, it was in its low state, and then it underwent some kind of change around 1935, brightened. We don't really know what happened here, unfortunately. There's no data. So there is every possibility that it could have gone down and back up between 1950 and 1980. But yeah, unfortunately, we're just going to have to take that one on faith and assume that it didn't. And then over here, we have the modern data with the transition from CFIT 1 to CFIT 2. So by looking at this historical data, Thomas managed to find a new event in Markarian 1018's past. And he did a bunch of periodic analysis to test whether this looked like it was strictly periodic or whether it was completely random. And he found that there was kind of some evidence of something like a period, but perhaps more like a characteristic timescale of around 30 years. So this fits best with the chaotic cold accretion idea, because something dynamical, you would probably expect to have a very well-defined period. So we come back to chaotic cold accretion, and we have a little scribble to kind of say in pictures what I said in words before, which is that in the high state, you have a very luminous accretion disk, and it's ionizing the entire broadline region. So the accretion disk is very luminous. That means we get this continuum emission, and it's sufficiently luminous to ionize the broadline region. And so that makes the broadlines appear brighter. So that's how we observe it in a type 1-esque state. But then when it goes down into its low state, the accretion disk is too faint to ionize the entirety of the broadline region, meaning that those broadlines disappear and the accretion disk dims a lot, meaning that we can no longer see it in the spectra. So why is this important? I talked about this before. We've got something that challenges, what's going on? Oh, it's okay. So we've challenged the unified model. We've shown that there is more to AGN classifications than just this perspective. Something evolutionary is going on as well. It is.
Yeah.
Says I'm bored of changing look AGN.
Yep.
It's not my fault.
This all looks good.
Should we just try unplugging and replugging? See if that works. That's not going to do anything to the Zoom, right?
So that's come back.
It just doesn't like the slide. It says your slide is ugly.
Yep.
Okay, we're back. Okay. Do tell me if it goes away again. Yeah, so we've shown that this is a challenge to the unified model. Shows that there's something else going on, and also implies that accretion is more complicated than we perhaps thought, which I didn't think was possible. And most importantly, this evolution on human timescales means that we can really test our theories. Like, I don't have to sit around for 100 million years and wait for something to happen. These things are changing on like yearly basis. And most importantly, this is going to help us understand the most energetic process in the universe. This is my pitch on why they're interesting. But the issue is that these things are not, well, historically, have not been systematically discovered. So the way this happens is exactly like the story I told you, where you observe something and then, oh, accidentally, the thing doesn't look like how you expected it to. Because there's no way for us to know, at least as far as we can tell, what galaxies are more likely to have changing look AGN. So we're entirely relying on serendipity to give us these objects at the moment. But this is where LSST comes in. In case you're not aware, the Vera Rubin Observatory Legacy Survey of Space and Time is going to image the sky once every 3 days. There's a bunch of brokers, which are essentially kind of packaged algorithms that are going to read in this enormous data flow and look for things that are interesting, things that are changing every night, and send alerts to astronomers when something that might pique their interest appears. And this is going to allow us to systematically detect changing look AGN in an unbiased way for the first time. Because the only way to do this is to look at all AGN to see which ones are actually doing this. And our predictions say that we should get thousands per year, given how many we have already. There's about 1,400 that have been observed to date, and that's, a combination of, serendipity, people looking at multiple epochs of spectroscopy, random chance. But with this system, we expect to find thousands per year. And so what we intend to do is use this. So imagine LSST is observing, or rather, Rubin is observing, and a new variable source is detected on sky. I get an email or a Slack notification or whatever I've set up that tells me, Rebecca, something like what you like has appeared in the sky. So then we want to search the historical archives. We want to search the modern archives, do some kind of clever calibration. Don't ask us too many questions about that right now. And output a combined light curve that has as much data as possible for this source to help you characterize what's going on. So we combine the data, and then that should allow us to model it. So by systematically detecting new changing look AGN, we'll finally be able to answer a bunch of questions that we haven't been able to before. The first and foremost being, how common are these? Because people ask me this all the time, and I'm like, ask me in 2 years. So we're going to be able to tell us this. What is causing them? Are most of them caused by chaotic cold accretion, black hole dynamics, obscuration, TDEs? Who knows? But we're going to find out. And kind of most importantly, how does this impact our understanding of how black holes grow? So hopefully I have made you interested in this highly dynamic field of research, and I'd be happy to take any questions.
Thanks for a great talk, Rebecca. Do we have any questions?
I just wanted to ask you about that don't understand the problem.
That's a good question. I'll just repeat that for those online. The question was, why can't we have more than one star causing a TDE? And that is definitely, you can totally have that. I should have mentioned that. If you can contrive of, a constant feeding of stars into the accretion disk, then totally you can have this last for years and years and years. I guess it's just the likelihood of that happening isn't particularly high. So.
You mentioned earlier that there is a good rule out there about binary black hole dynamics. With the galaxy we spent this time talking about, it was like it's possible there because it's merging galaxies. Is there like correlation? Merging galaxies, slightly higher chance. Is that something that can really be applied outside?
Yeah, so the question was, is there a correlation between merging systems and changing look AGN that might be due to a binary black hole system. And so this is an interesting idea, and I actually tested this 2 weeks ago. So thanks for asking. So I did a quick test on this. I went through the largest catalog of known changing look AGN that had good imaging, and I compared it to a large catalog of matched AGN from DESI that weren't known changing look. And I ran a test of whether there were more merger-like features in the changing look AGN sample, and the answer was resoundingly no, which I thought was quite interesting. Maybe I should publish that. Yeah, it was just like a random little test. But yeah, the distribution looked exactly the same.
Thanks, Rebecca. Lovely illustrated talk. Naive questions if I may. So, what is the evidence for the change in brightness, luminosity of the source actually being accompanied by a change in spectral time? We have direct before and after brightness visions, but we have complementary spectra in those epochs as well.
Yeah, so I guess this is where we're limited by the data that we have right now, because some of these things have been detected through spectra looking different, and some have been detected through sufficiently large changes in brightness. But not all of these systems have both. So people try and characterize these things into changing state AGN, which is this where there's something very different has gone on in the accretion disk, or just things that might be due to some other process. So I think we can't really answer that question until we have a sample where we have both the change in brightness and the change in spectra, which is what we want from LSST and hopefully follow-up spectroscopy. Yes, yes.
Just something else. So, to what degree might, especially in the early days of this sort of thing, see, the look at the spectrum would benefit on exactly where you place the slit. But there's a possibility that two people at the same time might have different instruments or whatever, some point to the same location, presumably potentially get different results. Looked galaxies. But I guess it's something you could check, you could verify, say, how much variation you expect a spectrum.
Yes.
To extract the flux from.
Yes.
Make sure that we can provide some faith in some of these earlier claims of changes in spectrum and not just some observation.
Yeah. But just to repeat, the question was, could an observational difference, like where the location of the spectrum cause kind of false flag changing look AGN? The answer is true. That's definitely true in the nearby universe, because the galaxies are sufficiently large that you could do that. But the majority of these things are at, well, high-ish redshift, like above redshift 0.5. So there's, yeah. So most of our spectra that we're working with are, you know, like 2-3 arc seconds. So for those, no, that couldn't happen. But for the very nearby things, and there are quite a few nearby, yes, misaligning your spectra could definitely cause that. But the way we follow up now with the nearby things is usually with IFUs to kind of get around that.
Thanks for your talk. Have you considered comparing sort of approach with that catalytic line? Because they have an accretion disk and they often go in. I guess here the accretion disk is often obscured and have direct access to it. And with cataclysmic binaries that I guess there's a reverberation mapping and but that seems more focused on the borderline region instead of the accretion disk. Can you access the accretion disk in some more, if you observe it more polarized directly to the disk? If you took time series spectroscopy of those, you could start to map out.
Yeah. So the question was, can we use techniques that are used in cataclysmic variables, which are much nearby with AGN. And I guess the answer is, to some extent, yes. The difference is here, everything that is going on in the nucleus is unresolved. So the broadline region and the accretion disk are the same point source on the sky. So these things are very unresolved. You can do time series analysis. So we have actually done a bit of time series analysis of the spectra of Markarian 1018, but it's quite complicated. And yeah, that's basically, yeah. So we do see variation in the broad lines with time. And yeah, we think that's probably to do with kind of the broadline region moving around. But yeah, so if you see a change in continuum, it has to be the accretion disk, right? So the broad lines can just be the broad lines. And that has, you know, a lag period of weeks to months, whereas the accretion disk is smaller. And so you can definitely observe time variability, but understanding it is where it becomes extremely difficult, because we're essentially, you know, we're trying to, because when I drew this diagram, right, that what we think it looks like, but we have no idea, really, right? Like that's just what we think from what we observe. We haven't observed this. So we could try.
Yeah, it's really nice idea.
Mm. Well, so the question there was, we have all this old data. Can we determine how common they are based on looking at known AGN with this this archival data? And the answer is sort of yes. So Thomas actually did this you did it for the whole CARS sample, which was 40 galaxies, and you also did it for a bunch of known changing look AGN that was sufficiently bright in the nearby universe. So the problem is that so Markarian 1018 is pretty much as faint as you would want to go, and this is redshift 0.04. So you're for the very long time series stuff, you do need to be fairly bright. But yes, so Thomas did do this, and you found significant changes in some fraction of known AGN. I've also been playing with this a little bit with ZTF data, just looking at things that are classified as just regular AGN, how many of those have significant variation, and it's more than you think. And so I think we're actually going to find, I'm just putting my bets in, I think we're actually going to find that changing this rapid variability behavior is actually quite common and is an evolutionary stage, between as an AGN ramps up or ramps down, you get this sort of behavior.
We have one last question. Yes, thank you for
There was outlet period between
Yeah, so the question was, why is there such a clump of data between 1930 and 1950? I have no idea. I would have thought there were more important things going on at that time. But yeah, I'm not really sure. It could just be that like some of the observatories went defunct after the 1960s or something, as they were building larger telescopes. Like I think they started to build bigger telescopes around like the 70s, right? And so 60s, 70s, yeah. So I wonder if the Harvard College observatories started closing down around then. But yeah, that's definitely, I have wondered that myself.
Thank you. Lots of very good questions.
Yes,
So
thank you for your questions.
Let's entertain our speaker outside for wine and cheese. Thanks.
Oh, and if you want a sticker, come see me.
Yeah.
in my other pocket? Is good?
Yeah.
Is that one got it?
Can't help
Is it?
Well,
This one.
Maybe that one's not real.
thank you. That was excellent.
Not sure if it is.
Oh,
Right.
that's my PhD student. She has to say that.
I'm gonna end the Zoom now. Bye,
Thanks
everyone.
everyone online.